My talk is simultaneous elevation of major cosmological tensions through lambda LsCDM model. Lambda S is for sign switching lambda. So what I will do, I will show you that with the simplest extension of lambda CDM that you may think, we can solve all the tensions. It is very simple model, but physically not simple. Okay, so sometimes we feel like this: if we have a big problem, we don't believe it can be solved in a very simple way. This is an effect, but I will try to convince you. Okay, so this my talk is based on joint works with John Barrow, Eleanor Di Valentino, Luis Escamilla, Suresh Kumar, Rafael Nunes, Emre Özülker, Alberto Vasquez, and Anita Yadav. So, so let me start with graduated dark energy. So little bit background. So if we apply from twice contracted Bianchi identity, we very well know that the coherent derivative of G mu Einstein tensor is equal to 0. In GR, this implies that the coherent derivative of energy moment tensor is also 0. From this, we cosmologists are used to see this thing, right? So this is local energy conservation equation. But you see, I am writing in a weird way. Instead of rho plus P, I am putting here var rho, because it is inertial mass density, which is rho plus P. Where do I know that? Because we cosmologists always see this equation in our papers and books, but we don't see this equation a lot. This is, again, we are getting this equation, which is a momentum conservation equation. It is, again, coming from Bianchi identity, because this is a special divergence of pressure, and this is for acceleration. So basically, this equation is Newton's second law of motion. Okay, so if you look at this term var rho here, it is like this is inertial mass density. So this is equivalent to F equals ma. So maybe inertial mass density is more fundamental quantity. It is quantity more fundamental than energy density. Why I'm telling you this? Because if you look at cosmological constant or the usual vacuum energy of quantum QFT, it defines perfectly the vacuum energy. Because for vacuum energy, inertial mass density is exactly equal to 0, independent of its value. Vacuum energy may have different values, but it's whatever value you think for vacuum energy density, its inertial mass density should be equal to 0. So for that reason, we were thinking that instead of if somehow vacuum energy is evolving, it is better to think that looking for its parameterizations rather than rho, var rho to inertial mass density. So the simplest extension could be, instead of using 0, using constant. We construct this model within 1 sigma. We found that inertial mass density is not equal to 0, but within 2 sigma it is equal to 0. But I won't talk about this. I will talk about graduated dark energy, which is the simplest dynamical deviation from 0 inertial mass density of the usual vacuum energy density. So this parameterization was inspired from John Barrow's paper, Graduated Inflationary Universes. It is from 1990. So, so this parameterization. So when you solve this, put this parameterization into this equation, local conservation equation, and solve it, then you will get this rho evolution. So this equation is interesting equation because it is very rich in giving you different behaviors. So, but the interesting thing here is that if you see this power here, 1/1 minus lowercase lambda, if this is a value that you can write as m/n, here m and n are odd integers. In that case, you can write this equation in this form. So you see there is a signal function here, which means that this energy density in this under this condition, and also psi here is a combination of here gamma and lambda, It is here. So, so this rho can change sign. Okay. So if lambda is less than 1 and gamma is less than 0, then under these conditions, energy density takes negative values in the past, and equation of state parameter of this dark energy will exhibit singularity pole during its sign change. So here is the equation of state parameter. So why this is important? Because we know from this first paper talking about negative energy density, this is Bose correlation paper, 2014. So they first discussed there should be negative energy density at redshifts larger than 1.5. So if you, and also following this paper, Shahni, Shapileo, and Stravinsky wrote this paper. So from brainwave cosmological constructions, you are getting equation of state parameter having this behavior, right? So it has a pole here, okay? So yeah, of course, if you think about negative energy density, this is physically sounds a little bit ill, okay? But we know such behaviors are possible even from Brans-Teke theory. If you look at Brans-Teke gravity extension of the standard lambda CDM model, which is here, you'll see you have pole here. So, I mean, this Jordan field is able to do it in the prototype modified gravity theory of Brans-Teke. Okay, so for this graduated dark energy, you see here is the rho d or rho critical 0. So if I choose lambda equal minus 10, it is giving this behavior. You see, so then you can put this behavior right here. Then you have all behavior here. Then this behavior can explain this figure you see here. And this behavior will give you this equation of state parameter behavior, which is similar to the one given by in this paper, which is from brainwave constructions. Okay, the good thing here is that if you have such a behavior, you see Hubble parameter here, the Hubble parameter, not Hubble constant. So at higher redshifts compared to lambda CDM, you will have smaller values of Hz, okay? And as a result of that, at lower redshifts, you are getting larger values of Hz compared to lambda CDM, which means that you can get also larger values of H0. But not only that, this model has no tension with Lyman alpha data. So we started to study on this thing because of the tension between Lyman alpha data point and lambda CDM. Then we discovered that it is also able to give you larger values of H0. So when we do cosmological using these Planck data, binocular acceleration data, supernova data, and cosmic chronometers. So if you look at this table, this is a very interesting table because if you have small values of lambda here, why it's important? Because you see this behavior here. So if lambda is getting larger negative values, this behavior you see here will be sharper. And if lambda goes to minus infinity, this function will approach the signal function. So then it means that you will have sign switching cosmological constant. You will have cosmological constant in early times, exactly. Then it will switch sign. And exactly switch sign. Okay. So you will have again negative cosmological constant, but this time it will be negative in the past. In this case, so when we concentrate this model on the above, you see lambda CDM, but you see if lambda is getting larger negative values, 0, -2, -4, then you start to observe bimodal distribution. So look at this figure, gamma here. So if lambda is 0, then the yellow curve, the peak is here, maximum is here. Okay, if lambda is -2, maximum is still here, but when you reach -4, you see maximum is still at the lambda CDM limit, but we start to observe here a new maximum, a small one. But when you come to -6, you see this, you have a maximum here. This maximum is larger than the other maximum, which is the other maximum is lambda CDM, limit of the model. So when you got even larger negative values of lambda, you preserve this maximum, but this maximum is moving to the right. Okay, but if I use this combination, psi, instead of gamma, psi contains both lambda and gamma. So let's see now, the maximum is here, which is lambda CDM. If you go to minus lambda minus 2, still you have maximum here, minus 6, 4, you see small peak here, new maximum, okay? So when you go to minus 6, you see this maximum. Then after minus 6, minus 10, minus 14, minus 20, you always find the maximum at the same point. So this is quite stable. So if from this function, e to the minus psi to the minus 1, we find z dagger. Z dagger is the redshift at which energy density changes sign. So you see it is quite stable. So this is very interesting. So which means that if you have rapid enough transition, then you are finding very stable new point away from lambda CDM. The point is this: if you are not brave enough to go for large negative values of lambda, you would never discover this maximum here. Then you would believe that lambda CDM is doing the best, but it is not like that. So, for instance, sorry. So how to go back? So how to go back? Just I'm going forward. The button. Okay. Sorry. All right. So if you see which one? Okay. So you have bimodal distribution. You see the chi-square difference reaches to 6. In this case, if you go to large values of lowercase lambda, so it is preferred over lambda CDM. So this figure will show it in a better way. For lambda 0, maximum is here, which is lambda CDM limit. So for minus 4, you see small peak here, and go to minus 10. You have new maximum here, then the model of this probability distribution. So this is more favored over lambda CDM. So you see now if you go to even minus 20, then you will have a very sharp behavior. So which means that if you have rapid enough transition from ADS to DS, you are able to solve, get larger values of H naught. It is apparent from here. So in the new maximum, you see H naught is larger. So, and you can see it here in this plot. So, but in this model, we were able to get values close to TRGB value. Okay, then what we thought, oops, again. So maybe we should skip this region because this is a lambda psi. This region, you'll see there is no stable value for lambda and psi. But if you are brave enough and come to here, you see a very stable point, which gives you z dagger, the ratio at which you will have energy density change, which is about 2. So instead, forget about this region. Let's focus on this region. If you focus on this region, if you see here, so this is pinker means it is more preferable. The model data prefer the model the pink more. So you have you don't have any tension with Lyman alpha data. This leads to larger values of H0 also. So if you look at this figure, you have almost constant energy density here, rapid transition here, then you have negative energy cosmological constant. So at the value 0.7 here, also it is minus 0.7 here. It is signaling exact sign switching lambda. Okay. Oh, really? Okay. So this behavior, we have studied different kind of dark energy models. We see such behavior in different models as well. And here there's model independent construction of interactive dark energy models. Again, we are seeing such a behavior in equation of state parameter here. So it is going up and coming back from down. So again, you have pole here. So the point is that we are able to see such behaviors from different models as well. But your model should be flexible enough to do it and rapid enough to do it. So, and theoretically, I understand this is not easy to realize, but it is possible. This recent paper here just appeared on arXiv, a theoretical one. They show that a classical metric signature change across boundaries with a degenerate metric in different combinations of generativity allows a classical solutions where the open DS patch can arise from a portion of ADS spacetime. So this is equations from this paper, exactly sign switching lambda. So we are also working on another paper these days. We are able to realize such a behavior by the contribution of extra dimensions. If you change the size of extra dimensions, it's possible to create such a effectively a cosmological concept that can change sign in four-dimensional effective spaceline. So the model in LsCDM model is simple model. Just you have at a certain redshift, you should have a sign change in the energy density of cosmological constant, then from ADS to DS. Okay, then we have exact solution here. The universe will behave like this. So guaranteeing that the model is becomes always consistent with CMB data, Planck data. We calculated that depending on Z-Dagger, how the model predicts, what value the model predicts for H0. So we see here that if H0 is around 1.8, we can reach Schu's measurement. Okay, this is happening because the Z-Dagger is very well constrained. If you look at this integral, you have Hz here in the integration. So if you have negative cosmological constant in the past, it means that Hz will be smaller compared to lambda CDM. To keep this integral constant, I mean, fix its value, you should have larger values of Hz at lower redshifts, right? So you see this behavior in this figure, okay? Lower H, and then you have larger H. So the interesting thing is that we calculated the predicted absolute value of supernova using this model. So we also, if Z-Dagger is 1.7, then the model from apparent magnitude of supernova, we are able to get exactly direct measurement of, Schu's measurement for absolute value of absolute magnitude of supernova. Okay, so here we constraint model using CMB and CMB BAO. Okay, so you see behavior here because we are describing Lyman alpha data. It gives you Schu's measurement. But when we add BAO data, this data point you see here doesn't allow model to go up. So the model has problem with this BAO data point from Z.38. So for that reason, model is not able to work perfectly. Okay, so but we see these results here. So if you don't use BAO data, we have H0 Z-Dagger like this, as we predicted in preliminary analysis. So interesting thing is that when H0 takes larger values, S8 also gets smaller values. So a potential model can also solve a S8 problem and also MB problem. So these are three major tensions in lambda CDM that are basically this model is able to address these three problems simultaneously. So we further analyze the model. So instead of using BAO data to break the degeneracy between H0 and Z-Dagger, we could use Pantheon data also. We investigated it and using also MB prior. So with the model predicts, if you don't use full BAO data, for instance, CMB, Pantheon, Lyman alpha, and MB prior, the model, the Bayesian evidence is 12. It is which number, okay? So, and you see here, let's see this panel here. So this is Schu's measurement. The model predicts this exactly Schu's measurement. There is no MB tension. There is no S8 tension. And we explore some other less significant tensions. They are not also exist in this model. So I'm finishing very quickly. So let me skip this. Okay, we noticed that only model has problem with two data points in 3D Bayer data, then we, instead of using 3D Bayer data, which is model dependent, we decided to use 2D Bayer data, which is less model dependent. The surprise is that when we use 2D Bayer data, we got this result. So, this, you see this contour here is just from Bayer transversal data, and this blue one is from CMB constraint Planck, and when you use both of them, the green one, the model predicts exactly the intersecting exactly where the shoes measurement. So this, we thought this may not be just a coincidence. So then we further investigated SH tension using KITS data. You see, when we constraint model using only KITS 1000 data, you see exactly the same contours because the model is exactly lambda CDM. Model is exactly lambda CDM. Before and after the transition, still you have lambda CDM. Only lambda is what you do. So you see the tension for lambda, standard lambda CDM, but in lambda CDM model, this contour injecting into this blue green contour. So it means that you don't have SH tension anymore. 2 minutes. Sorry.
No,
Okay,
is that the people have to reach the restaurant.
Okay. So there are some results. So the point is this: if you Z dagger is around 1.7.
The problem is that the people have to reach the restaurant.
Sure.
They already leave with many. So go to the conclusion.
I came to the conclusion. So if you have a sign switch in lambda, so basically all the tensions, known tensions in lambda CDM goes below 1 sigma. And so the last three figures. So comparison of two models. So this, if you look at the baseline free parameters, they are slightly different. But if you look at derived parameters, they are completely different. And last figure, if you use lambda CDM, when you add extra data points, you see the contours are moving in different directions. But when you have sign switching cosmological constant, look at the baseline free parameters. When you add new data points, contours doesn't move. They are quite stable. And if you look at the derived parameters, they are smoothly, very nicely approaching 1.7. And the Bayesian evidence difference is, this is the highest Bayesian evidence difference in the literature so far, which is 20. When we use full data point, the Bayesian evidence difference is 20 and chi-square difference is 40. So thank you for listening to.